Hi, I'd like to welcome Randall Smith. He's an astrophysicist at Johns Hopkins University and NASA Goddard. And we've known each other for many years now, and that's meant many great late night conversations about cosmology and X-ray telescopy, the same things that he's going to tell you about today.
Thanks very much, and thanks for the invitation to come and talk to you about this. Now, in preparation for this, I, of course, looked at a couple of previous things on videos.google, and noticed that the folks from Hubble showed up with a really cool video that they had put together of various Hubble shots. So I come from the X-ray group at NASA Goddard and couldn't resist, therefore, showing a homegrown video. This is actually, the singers are from local people, if the music comes up. Yeah, not getting any, no sound. Yeah. We'll restart. It's a shame.
X-rays, gamma rays, high energy. Hot stars, heavy stars, high density. Quasars, black holes, supernovae. Powerhouses lighting up the galaxy. Flashing, bursting, pulsing objects we could see if we had X-ray eyes. If we had X-ray eyes. Going up the spectrum, repeat after me. Radio, infrared, visible, UV. Keep going all the way, and what do you see? That's X-rays, gamma rays, high energy. An X-ray photon has a high frequency, which means a shorter wavelength than you could ever see. High energy radiation. High energy radiation. X-rays come from various processes, like a cloud of gases above about 1,000,000 degrees, or magnetic fields that send electrons swarming like bees, or even neutron stars emitted like black bodies. And you get X-rays from stars, stuff that came near to and fell into a black hole's gravitational potential well. If we flew above the atmosphere and looked out at the skies, and if we could do it with X-ray eyes, we'd see more flashing and popping than you realize. Objects winking on and off like fireflies. The X-ray sky isn't calm and quiet. It's more like a rockin' high energy riot, yeah. X-rays, gamma rays, high energy. Hot stars, heavy stars, high density. Quasars, black holes, supernovae. Powerhouses lighting up the galaxy. Flashing, bursting, pulsing objects we could see if we had X-ray eyes. If we had X-ray eyes. X-rays can show you the roots of your teeth. Shine them through your body, see the bones underneath. But don't go thinking that we X-ray the stars, 'cause they're billions of miles away, much too far. We collect all the X-rays that they send to the Earth, telling tales of star death, giving hints of starburst. X-ray binary stars. X-ray binary stars. Here's a story of a pair of stars called Cygnus X1. One's a black hole many times the mass of the sun, with a disk of gas surrounding it, spiraling in, sucked from their companion stars' outermost skin. We see the high-speed flickering as star stuff flies in, a one-way trip beyond the event horizon. A cosmic lighthouse flashes in space. It's an X-ray pulsar with a regular pace. A neutron star 30 miles around at best, spinning round its axis once a second or less. And way beyond the Milky Way, the active galaxies are the furthest, biggest things our X-ray eyes can see. Point your X-ray specs towards the sun's location. You'll notice that along with its slow rotation, you'll see active loops and plasma arcs in a solar dance producing X-ray sparks. The X-ray sun isn't serene and smooth. It's a dynamic and changing high energy groove. High energy groove. High energy groove. X-rays, gamma rays, high energy. Hot stars, Powerhouses lighting up the galaxy. Flashing, bursting, pulsing objects we could see. If we had X-ray eyes. If we had X-ray eyes.
Okay. That was actually sung by a group of a cappella vocalists in my lab, a collection of astrophysicists and other folks, and they're both excellent singers and excellent astrophysicists. But today I'll be talking to you about the steps that we're hoping to go on beyond. The video talked about RxTE, which is a previous generation NASA satellite still orbiting and doing a great job. But we have big plans to go beyond that and build a whole new fleet of telescopes looking at X-rays, gravitational waves, other kinds of things out there that we have now learned that we desperately need to know about. So I'm going to do a quick review of a lot of cosmology and a lot of the universe that we've learned about in the very recent past. And I do mean recent. I actually went back and complained recently that the entire cosmology course that I took when I was in graduate school is now out of date, and I wanted my money back. But here's one of the things that we've learned. This is a baby picture of the universe taken by the Wilkinson microwave anisotropy probe. These are the residual fluctuations left over from the Big Bang. We've taken away the DC component of this, and this is the part that's down by a factor of 1,000,000 from that, showing you the fluctuations. These are the little tiny dots and bubbles, and each one of these things here is eventually going to grow up to become a super galaxy cluster. The little tiny dots here are going to become galaxy clusters, and these voids are going to grow up to become giant voids in space. So this is sort of a picture of the early imprint of what the universe is later going to become, as far back as we can possibly look in optical light. We've also been taking deep X-ray images. This is a picture from the Chandra X-ray deep field. Deep here means that I think this is 2 million seconds worth of observation, which is approximately a little less than a month. Each one of these dots here is actually a black hole, usually at the center of a galaxy. So this is some supermassive black hole that's sucking in matter at the center of the galaxy. And here is a simulated image in X-rays of what that might look like. You can see that it's brighter on one side and dimmer on the other. That's simply because of both Doppler shifting and the effects of relativity, so that the part that's coming closer to you gets relativistically beamed and becomes brighter, while the part that's going away gets dimmer. We've also been working on, and this is a lot of work has been coming out doing on this in California, Caltech and other places, on measuring very distant supernovae. But not just any supernovae, specifically type 1a supernovae, which have this amazing quantity that they, after you do some fudging of the numbers, they all seem to be about the same brightness. Or at least you can scale them so they look like they have the same brightness. So they are very good standard candles, so-called. So we know how bright they are, and if we can then measure how far away they are in terms of redshift, we can then calculate how bright they are, and we can get an idea of how the universe has expanded since the time when they went off. That's given us some real surprises, which I'll get into just in a moment. Now, this is a shot from the Hubble Space Telescope, and you can see here two galaxies that are in fact in the process of merging, which is a really dramatic process. Now, one of the things that we know from both optical and X-ray observations is that most galaxies, and quite possibly all, although we don't know that yet, whether or not all have supermassive black holes at the center of the galaxy. We know that our galaxy has a supermassive black hole. It's actually about 1,000,000 times more massive than the Sun. It's called Sagittarius A star because it's in the constellation of Sagittarius, and A and then star because it was some weird object when it was first discovered. Nobody knew what it was. We now have a really good idea that it's in fact a supermassive black hole, probably the only one in our galaxy. Well, you might ask the question that if you have two galaxies that merge, what happens to their black holes? And in fact, now with Chandra, we can image that, and we can in fact see places where we see two black holes orbiting each other at the very center of a galaxy. You can imagine what happens when those two things hit each other. And I'll get into just that. I have a simulation to show later on of what that might look like. So the title of this talk, though, is Beyond Einstein, and to those of you who've heard marketing ploys before, this might sound like one. And to an extent that it is, but it is also a very realistic description of what we're trying to do. Einstein was, in 1905 came up with special relativity, then just sort of blew us all away with the following year's work on general relativity. We have been, in some sense you could read modern physics of the last 100 years as catching up with what he's done. But three of the things that he predicted was the expansion of the universe. Now he actually predicted it, worked out the calculations, and then said, well, that's probably wrong. So he put in a fudge term called lambda in order to make the universe stable. Of course, a couple years later, somebody actually showed that the Hubble actually showed the universe was expanding, and therefore Einstein would have been perfectly correct to leave that in there. He was always kicking himself, calling his greatest mistake to put in this extra term. And we've always thought less of him because of that, really. It's really hurt his reputation. He also predicted the theory, general relativity comes up with black holes, although he was neither the person who worked out the original mathematics of them, that was Schwarzschild, nor the person who named them, that was Wheeler. And this cosmological constant was the term that he came up with in order to stop the universe from expanding all over the place or collapsing. Now, the great thing is here's Hubble's discovery of the expanding universe, and you can't really see the dots on that, but they really do line up very nicely. I mean, when Hubble came up with the idea that the more distant you are, the higher your recession velocity is going to be, it worked out very beautifully. The data sort of demanded an explanation. And here's an artist's conception. Unfortunately, that's all we have right now for what the black holes at the center of our galaxy might look like. This is the accretion disk of material that's feeding into the black hole. That's obviously the surface, so-called, of the black hole itself. These are all things either coming out of the black hole or they're actually just sort of not optical illusions. They're bent by the gravitational field of the black hole itself. So this is sort of the back half of the accretion disk that has been pulled up into our line of sight as a result of the massive black hole's gravity. And finally, we now have evidence for an accelerating universe, which is, I got to say, one of the strangest things to come out of cosmology in some time, and that's saying something. The accelerating universe is something I'll talk about in just a moment. But it's strange. It's really, really weird. But with all this, we really don't have the complete picture. Einstein gave us a lot, but we've learned things, especially this accelerating universe stuff, that have made us question whether or not we know the whole picture. As a matter of fact, we're certain we don't know the whole picture. That's the goal of the Beyond Einstein program, is to sort of figure out what it is we're missing. The series of missions will hopefully answer the questions down here. What powered the Big Bang? Where did it come from? What happens at the edge of a black hole? And what is the mysterious dark energy pulling the universe apart? What is doing that? Where did that come from? Who, in the words of the physicist Rabi, who ordered that when told of a new particle? The question about what powered the Big Bang, there's the Big Bang. We're not going to learn anything about the Big Bang itself. It's too far back. Too many weird things happen in between us and it. This is the Big Bang plus 300,000 years. That's the so-called surface of last scattering. As far as optical photons are concerned, as a matter of fact, photons of any kind, X-rays, gamma rays, radio waves, anything, beyond this point, the universe was basically ionized. It was a dense ball of hot ions, electrons, protons, and so on. The photons were scattering all the time. So we have no chance of ever seeing back before this point of the universe because the universe was optically thick at that point. It was as though a sheet was dropped in front of us between me and you. You wouldn't be able to see me no matter how hard you looked with how big a telescope. There just is no data optical from photons that comes here. However, gravitational waves do come from before that. We can look back well before this period if we can use gravity waves to do it. All we have to do is build a detector that is sensitive to gravity waves. Okay, so it's a big but it's doable. Next question is, what happens at the edge of the black hole? This is the picture I already showed. Here's a different simulated black hole image. We would very much like to know what's going on at the edge of a black hole, largely because it is very, very difficult to test Einstein's theory of general relativity here on Earth. You need to have in order to test what's called the strong field limit, the very extreme areas of Einstein's theory of general relativity, you need to have something like a black hole going on, and they're very hard to get into the lab. I mean, OSHA standards and requirements are really bad with black holes. So as a result, we need something that we can look at general relativity in sort of its natural habitat around a black hole. And that's what our real goal is here. And finally, this dark energy stuff that I've already mentioned once. And here's the part that's just strange. I'll just read this. In the standard cosmological framework, the acceleration of the expansion of the universe is caused by dark energy that makes up 70% of the mass energy density of the universe today. Now, here's a couple of weird things about that. If we went back a bit in universal time, say we went back to when the universe was half as old as it is today, dark energy would make up a very, very small portion of the mass energy of the universe. It would be almost totally undetectable. If we go forward in the universe a couple of foldings, you know, if we wait for another, say, 10 billion years, 20 billion years, dark energy will totally dominate the mass energy of the universe. Basically, all of the energy in the universe will be in the form of dark energy, and actual matter like we know of it today will be negligible. So we, for some reason, are living at a point where dark energy is a significant portion, actually probably the dominant portion of our universe, but it isn't totally dominant, nor is it totally negligible. This is something that has people a little nervous. Anytime you have a theory where A, it includes stuff that you have no idea about, and it seems to be needed to be tuned in just the right way in order to work right, suggests that maybe you don't have a total grip on the theory. And I would have to say that almost all of the people who work on this for a living, I'm not a cosmologist, I simply talk to people who are, think that, well, okay, this theory is working well for us, and we're certainly not going to ditch it now because it explains a lot of things. But on the other hand, putting 70% of the mass energy of the universe into something we don't understand anything about is disturbing. It's an opportunity for somebody to come up with a new idea that works better. There are some possibilities. One explanation for dark energy is Einstein's lambda constant. You can actually work it up. You can get it to work that way. Everybody sort of agrees that would be the most boring way for dark energy to work because there's no theoretical reason why there should be a lambda that is this particular value. And if it turns out that it is just that value, it'd be very, I think people would call that disappointing. What we're really hoping is that maybe it varies with time. So if we look back, we see changes in the acceleration of the universe. Or that maybe general relativity is wrong, the standard cosmology is wrong, something. So I'm talking about 70% and so on. So what exactly am I talking about? And so here's sort of a census. This is an audit of the material in the universe. So if anybody ever asks you where the laptop is going, you can say, that's part of the 0.03% of the universe that's made up of heavy elements. Heavy elements means anything heavier than helium. To an astronomer, metal is anything heavier than helium. There's hydrogen, there's helium, and then there's metals. And that counts for 0.03%, and that's why we don't make any much division between the different ones, because when something is that small, who cares anyway? Then there's neutrinos, and that's 0.3%. So not trivial. I mean, there's some neutrinos out there. There's billions of them in this room. They're passing through our bodies as we speak. Although I didn't notice that there was not a sign warning me about that when I entered the room, that maybe the state of California hasn't determined they're cancer-causing yet. Stars, 0.5%. So there is a fair amount of material in stars, but that's hydrogen and helium. And then there's free hydrogen and helium that hasn't made it into stars, or maybe it made it into stars and then it came back out again. That's 4%. So, you total all this up, we got like 5% here in stuff that we would recognize as matter. Dark matter. Dark matter is not one of these above. So it's not hydrogen, it's not helium, and it's not anything, regular matter that's heavier than hydrogen or helium. It's not part of the periodic table. It's not an electron. This is something totally different. It doesn't interact via the electromagnetic or the strong force. It interacts via the weak force and gravity, so far as we know. We do not know what this particle is. We do know from lots of different observations in lots of different contexts that it exists. So there is dark matter out there. There's dark matter holding our galaxy together, for example. Our galaxy would not rotate the way that it does if there weren't dark matter. And so for a long time, people were sort of moderately unhappy about dark matter. There are lots of dark matter searches going on, trying to find out what the dark matter is. And so that was the goal, is let's find out what the dark matter is. And then suddenly somebody comes along and says, whoops, we just found this dark energy stuff. That takes up 70% of the matter, which, relegating the dark matter problem to a minor little correction term, it also means now that you've sort of invoked the tooth fairy twice. This is always a problem in any physical theory. You're allowed to invoke the tooth fairy once, okay? And that's the dark matter. Now that we've got 2 in there, all bets are off. Now, I've been talking about this. How do we actually know this stuff exists? This is the advanced version. This is the Hubble diagram on steroids. It's one of the most recent ones that we've got. This is on this axis of the graph here, and this is just a blown up version of this one down here. This is the redshift, or linear scale of the universe. Larger redshift, further back in time. So redshift of 1 means that all wavelengths have doubled in scale by the time they get to us. Redshift of 1/2 means that they've gone up by 1.5 times. So a photon with a wavelength of 1,000 angstrom would become, say, 1,500 angstroms or 2,000 angstroms if it came from a redshift of 1. So this is going back in time. Here's sort of nearby stuff, and here's its brightness of those type 1a supernovae that I was telling you about. These are the things whose brightness we think we know pretty well. And so we can then therefore say how bright they should be for given how far back they are, just distance, because things get dimmer as they go back in time. So here's the plot, and you can see that basically it's working just great out to here, working reasonably well, but now we're leaving the sort of standard, the lines are diverging. The red line in here, the top red line is a universe that will expand at the critical density and doesn't accelerate. Lines down in here are universes that will eventually collapse again into what's something called the big crunch. The universe then finally collapses and turns over and falls back into itself. Then these blue curves here are the accelerating universe, and this is the stuff that nobody understood, that somehow the universe is not only getting bigger, it's not just sort of coasting and getting bigger, it's accelerating. Something is driving the universe to bigger and bigger scales. And the only thing that really do that is what's called vacuum energy, which means that the vacuum of space itself has a pressure of its own. So you make an empty piece of space, and it's trying to press to make more space. And as you can imagine, that's a process that becomes exponential, obviously, immediately, which is one of the problems with that 70% number I told you about. If, in fact, the universe is filled with stuff that has vacuum energy, and it's every time you make some more space, it's filled with more stuff that we don't know about that's somehow trying to make more space, well, that's going to take off and suddenly and very quickly dominate the entire mass energy of the universe. Everything else will be totally negligible. We just don't know what that stuff is. We'd very much like to know. Here's another graph of that curve. In case you were a little not totally convinced, here are the data points on a different way. Here's today, here's nearby stuff, and then you can see that the supernovae that we're seeing are much closer lying on this curve where initially the expansion of the universe decelerates, but then suddenly this vacuum energy takes over and just starts blowing the thing up. So the universe seems to be in the process of blowing itself up. We just don't know why. The Beyond Einstein program is in part designed to answer that question and some others. The program consists of a whole series. I mean, isn't this a beautiful diagram? Just admire that. I didn't make it. This is the 2 big projects. One is called Constellation-X, and I'll talk a bit about that. That's a new X-ray telescope designed to look at black holes, other X-ray sources. This is LISA, a gravitational wave detector, series of 3 telescopes with lasers going between them. I'll talk about how that's going to be able to detect gravity waves. There are 3 sort of smaller projects. One is called the inflation probe. That's designed to try to look at the very earliest part of inflation in an indirect fashion. It's not by measuring the gravity waves themselves, but in an indirect way by measuring the polarization of the light that comes back from the Big Bang and hope to get a grip on the gravity waves that way. One called the dark energy probe. That's to actually try to get to grips with what that dark energy stuff is. And a black hole finder probe in order to get a good idea of whether or not black holes are at the center of all galaxies, and if so, why? What's making them? What are they doing? What's going on in there? Those then lead to 2 sort of what are called vision missions that are more distant future, but we'd very much like to do something. For example, we theoretically know how to build a device that would actually image a supermassive black hole in another galaxy. And when I say image, I mean take a picture of it. An actual, 4x6 snapshot, send it home to mother, picture of a black hole. Now, we don't know how to make it today. Give us 30 years and we probably could. And the other one is to actually do a Big Bang observer to do an even better job of this inflation probe to come to grips with how the universe was actually born. So, the Constellation-X mission. This is the one that I'm directly involved with, so I know the most about this, but I'll try to give equal time to all the other missions as well. X-ray observations must be in space. The reason is X-rays don't travel in the atmosphere. If we set up an X-ray telescope here on Earth, the X-rays simply wouldn't come down to us. So we need to put it into space. We need it to be as big as we possibly can make it. So what we decided to do was to build 4 identical telescopes and bunch them all together. You might ask, why not just build one telescope? And it turns out that it's easier to build 4 smaller ones than it is to build one big one. We orbit the sun at the second Lagrange point. This is a bit of a race. The second Lagrange point is becoming a very busy intersection. Lots of countries and satellite builders want to put things there because it's near to the Earth, but it's not too near. You know, it's like the suburbs. You know, it's a good location. Commute isn't too bad. It's quiet. This will allow us to do X-ray imaging and high-resolution spectroscopy. So we'll actually be able to tell with really good precision where that light is coming from. We'll be able to tell Doppler shifts of, for example, light coming from the very edges of a black hole. It's substantially more sensitive than the current facilities, and we'll do those things. Here are some examples of the kind of stuff that we're going to be looking at. Here is a plot of the X-ray energy versus flux, and it turns out that the accretion disk around a black hole, that bit that you saw swirling around, has a certain amount of iron in it. And that iron emits what are iron fluorescent lines. They're 6.4 keV. They just happen to be the line that emits from iron when you heat it up to or when you hit it with a hard enough electron. Well, if that's normal and it just emits a normal, everyday spectroscopic line, just, you know, think there. What's happening here, the reason it looks so funny, is because it's going around a black hole very near the Schwarzschild radius of the black hole. It's orbiting very, very close to the black hole itself. And if the black hole were just a normal Newtonian object, it were just, you know, some massive object that didn't have all this special relativity and general relativity going on, this curve would look sort of like this. It would look like a double-horned shape, just because of the Doppler shifts involved. Now, because it does have general relativity and special relativity involved, the part that's coming towards us gets enhanced a bit. The part that's going away from us gets decreased a bit, and you end up with this sort of funky little shape here. So if you think about it, what this means is that this is data from the OSCA satellite, and it was a very difficult observation to get. When you make a telescope that's 100 times bigger, you can get this kind of data much, much easier. And if you think about this is used to prove that that's what we were seeing, but if you imagine getting 100 of these, you know, every hour or something like that, that means that you can start to map where this iron is going around the black hole. And this is the iron that's about to fall into the black hole. So this is basically telling us what's going on right there at the edge of the black hole, right before it falls in. Just another thing that we can learn about black holes, and this is sort of a strange place to talk to have it, we're also going to be looking at black holes merging with each other and the process of spiraling in, merging, and then sort of the final ring down. This is a process that we don't know that we can observe this yet in X-rays, although we'd very much like to. We can see the massive numbers of gravitational waves that come off of that process, and I'll talk about that in just a moment. So one of the goals of CONX is to look at these black holes spiraling, you know, matter spiraling into the black hole. We'd also like to know how black holes evolve in time, because we're not quite sure where all the different masses of black holes came from. Do they come from, are black holes created sort of small and then they just accrete over time, or do they get bigger over time, or do they start off big? We don't really know. If we could take observations at a series of distances, we would learn a lot more about how they actually come about. We're hoping to also do some work on dark matter and dark energy with Constellation-X. This will be done via other techniques, looking at, for example, clusters of galaxy to trace where the matter is coming from, what the masses are, and thus figure out how far away they are. And finally, look at things like the origin of the elements, look at supernovae, stars exploding, because with Constellation-X we'll be able to look at all the different elements coming off of a black hole at once. Sorry, black hole, no. All the elements coming off of a supernovae as it explodes. Leaves a black hole in the center possibly, then all the material coming out. We can look at elements as they're forming. So here's a picture of what that accretion disk looks like. So here we have, you know, the various matter swirling around the black hole. This is what's called a hotspot, a flare. We don't really know why they occur, but we do see them. Things just sort of get brighter and then dimmer, brighter and then dimmer. And so imagine tracking these as time goes on. And it's a little hard to see down here, but this is the line shape that comes out, and you can see that it varies all over the landscape as these things fall into the black hole. We can make a map over here of energy versus time, and here we have time in seconds, so that's 10 seconds, 15, 20, and you can make this sort of waterfall diagram. This diagram will tell us things like how fast the black hole is spinning, what the mass of the black hole is. This is how we can actually test to see whether or not Einstein's theory of general relativity works or not at its most extreme case, in the center of a black hole as things are falling into it. Moving on to LISA. LISA is brand new technology. We have built X-ray telescopes before. This is the Constellation-X is a much bigger telescope. It has new facilities, new detectors, new ways of doing things, but in some sense it's a bigger version of things that we've already built. LISA is brand new. LISA, the way it works is it's got 3 spacecraft, 1, 2, 3. They are separated by 5 million kilometers apiece. It's a 3-armed interferometer with a baseline of 5 million kilometers. Nothing like this has ever been built. Nothing like this could be built on Earth. It has to be run in space. It's got each one of these spacecraft here is sitting there pointing at the other 2, and they have 6 free-floating proof masses, they're called. And now you might wonder what that means, and really all it means is a proof mass is a little tiny square of a metal alloy that is going to be free-floating in space. It's not actually connected to the spacecraft. The point of the spacecraft is to signal data down from about the position of that little piece of metal, and to stay out of its way so that it doesn't actually touch the walls, because if it did, it would throw off the entire measurement. The goal is to measure the positions, the distances between all of these proof masses, here and here, as a function of time, to a precision of 5 picometers over 100 seconds. So this is substantially smaller than an atom. Atoms are something like 0.1 nanometers. So this is 5 picometers. We're way down there in size scale. The idea is that you can see a gravitational wave coming through, distorting space and time as it does, changing the distances between these proof masses as it goes. So if, for example, a black hole meets another black hole somewhere halfway across the universe and sends off gravitational waves as a result of its merger, this system would see the ripples in space and time that came halfway across the universe and change the distances ever so slightly. As you can imagine, the data analysis on this project alone is quite an effort. We haven't launched it yet. They've already gone through 2 rounds of analysis of simulated data to try to figure out how to do all the data analysis in order to pull things out from this. If you'd like to get involved, actually, they're looking for anybody who's interested. The data sets by Google standards are pathetically small. I think the entire thing fits on 5 gigabytes is the entire mission's worth of data. But all the data you get are the lengths between these 3 arms and a measurement of the error in that measurement, and you're expected to deconvolve the entire universe as it's going on around you. So the goals of LISA, besides just to show that you can do this, this will be the first actual measurement of gravity waves that humans have ever done, is to determine the role of massive black holes in galaxy evolution. We'll be able to see the massive black holes as they start merging in things. Precision tests of Einstein's theory of relativity. It doesn't get more precise than this. We're measuring the gravity waves that his theory predicts. We'll also see ultra-complex binaries in our galaxy. That's sort of the background radiation for us. For this is a series of small binary systems in our galaxy. We're going to see things like supermassive black holes, intermediate mass black holes, maybe as they're growing to become supermassive black holes. Intermediate mass means like 100 times the mass of the sun, maybe. And if we're very lucky, we might see the cosmological background. So now, one of the big things about this, and this just happened in about the last year and a half, this was a huge advance in the theory of general relativity numerical calculations, is we're building a detector whose main point is to see the merging of 2 black holes. That's the real goal of LISA. So you'd sort of like to have a theoretical calculation of what it's going to look like. It would make everybody feel much better if you actually had an idea of what you were hoping to see. Well, the problem was that problem, the so-called two-body problem of general relativity, solving two equal mass black holes rotating around each other until they merge, had been an ongoing problem for at least 20 and probably 30 years. I'm not sure the exact number. People have been working on this problem for a long time. And not just a few people. I mean, hundreds of people had been working on trying to solve this problem with very little success. It got thrown onto computers very early. For a while, the computers simply weren't adequate to do the problem. Then the computers got to be adequate to solve the problem. They would put in everything that was known about general relativity into a mesh code. They would run it numerically, and it would crash. And then they would fix the crash, and they'd run it again. It would go a little bit further, and then it would crash. And about a year and a half ago, they solved it via a series of really clever techniques. And if you'd like to know, I know a little bit about it. If you want to know more than just a little bit, I'll direct you to the person you should invite. But to come give a talk about it, this group here has been doing a huge amount of the work. So this is a movie of what two black holes, black hole and black hole, look like as they merge with each other. Let's see if this works. And what you're seeing are the contours of constant gravitational curvature. So these black holes are spinning, which is causing them to be non-symmetric. Now you're seeing them, you're sort of going back a bit, and you'll see the red waves of the gravitational waves coming off of it. And that's time and space distorting as you're looking at it. And then you come back in, and you can see the residual, what's called ring down, of the merged black hole, emitting a couple of gravitational waves coming off. The amount of power that's coming out of here is immense. You get approximately 3 to 4% of the total mass of the system coming out in the forms of gravitational waves. That is, during the time that it's happening for supermassive black holes, brighter than all the galaxies in the universe combined. The amount of power coming out of these things. I checked, and you might imagine, for example, how are you going to do this data analysis problem from the LISA data? It's going to be amazingly hard. Everything is adding together. Well, the answer is if, in fact, one of these happens, which they hope to see maybe about somewhere on the order of tens per year, they'd really like to see, it's going to look like this in the data. Basically, from what I was told, the data analysis of an actual supermassive black hole merging in the LISA data can be done by eye. You just look at the data stream and, oh yeah, there's one. So the Einstein probes, these are the smaller missions. CONX and LISA are the two big missions that are part of the Beyond Einstein program. The Joint Dark Energy Mission, aka the Dark Energy Probe, is designed to determine the evolution of dark energy with time. This is trying to map out, is it constant in time? Is it changing in time? Give us any idea as to why it might be this 70% large number that we have today that we don't understand. This is a partnership between NASA and the Department of Energy. It turns out the Department of Energy funds a fair amount of this sort of basic physics research, and they're interested in the problem as well. This mission doesn't have a design yet. There are actually 3 competing designs right now for this mission, doing the problem in slightly different ways. So I can't tell you how it's going to be built because it's not actually known yet. The same is true actually for all of the probes. The inflation probe is designed to look at the early imprints of the period of inflation when the universe sort of blew up to its sort of semi-present size, and to see the imprints of that are left on the cosmic microwave background radiation, which is that blurry picture I showed you at the very beginning. The idea is that if you look at the polarization of that, you might be able to get to grips with some of the gravitational waves that were created earlier on, and to sort of get a lever arm to see back further into time and understand how inflation happened. And finally, the black hole finder probe. And in some sense, this sounds very simple because all we want to do is use this to find black holes, to identify them in galaxies. But there's a lot of work that just needs to be done statistically. We just need a large enough sample of black holes in order to answer some basic questions about them. How do they grow? Why are they always in the center of galaxies? Do you ever see galaxies or black holes at the edges of galaxies that are moving in? Are they mergers? Where do they come from? All these questions, in order to answer them, we really need statistics. We just can't look at 1 or 2 and answer the question that way. So the 3 methods, the 3 possible ways of doing the dark energy probe is, the first idea is, well, we found dark energy by looking at type 1 supernovae and measuring how far away they were and how bright they were, and thereby learning about the fact that the universe seems to be accelerating. Well, one method is to simply do more of that. It worked before, let's do more of it. Another one is that the very early universe had acoustic waves, basically sound waves, that were bouncing back and forth back at the earliest days when the universe was a giant soup of plasma, hot electrons and protons, and we couldn't see in it. It still had variations. It still had things bouncing back and forth. And those would lead to acoustic signals. And those would suddenly die out when the universe went from being an ionized plasma to being a neutral plasma. So you go from this big ionized mess, which is bouncing back and forth and ringing like a big explosion, and then suddenly it dies out. Well, it leaves you with the acoustic signature. Those sound waves stay in the signal. And those sound waves end up being the things around which galaxies and galaxy clusters formed. So if we measure simply where galaxies are in space and position, then we can invert that using a Fourier transform, basically, simply enough, to come up with what that acoustic signature was and thereby learn something about what dark energy was doing. We learned something about how the universe was made. And finally, we can measure galaxy cluster masses and then figure out how far away they are by using something called weak lensing. This is using the fact that large masses themselves actually bend light. And you may have seen famous pictures of galaxies that bend into big, what are called Einstein arcs, which are big circles around some galaxies. Well, there's also a process called weak lensing, which is just looking at the signal from distant quasars as they go around galaxy clusters. And then you invert this process and you can get an idea of what the mass of the cluster is, and thus invert the entire problem and come up with a measurement of dark energy. 3 different techniques, and basically there are 3 different probes. You'll be shocked to hear that one probe is trying out each technique. There'll be a competition and somebody will win, and we'll launch that probe. The inflation probe, I'm not going to go into too much. Basically the idea is, as I said, to measure the polarization on this map, and thus to go back even further and learn more about what's going on in this map. And then here is the black hole finder probe. The problem that we have with looking for black holes is that most of them we think now are surrounded by these disks of stuff accreting onto the black hole. And that's pretty straightforward. We have what's called the unified theory of AGN, which says that all black holes look basically like this. The problem is one mostly of geometry. If we're looking down the jet, then we see what's called a blazar, and the black hole can't be missed. It's incredibly bright. We're seeing this huge jet of material coming straight at us. If we're looking at the side of the accretion disk, though, we don't see anything at all in most wave bands because it's absorbed by the accretion disk. About the only thing that we can see is if we look at very high energy X-rays, which can penetrate this thick disk of material, and then we can get an idea of what's there. So strangely enough, actually, we think the problem with understanding the galaxy, the center of galaxies and what's going on, is purely one that sometimes the black holes are pointing towards us and sometimes we're seeing their edge. And as a result, we only learn about the ones that are pointed towards us or the ones that are easy to see. We don't learn about the whole sample of black holes out there and what's going on with them. So the question is, will we do this? Well, unfortunately, each one of these missions is sort of pricey. Now, I mean, I'm not talking like Palo Alto house expensive, but they are sort of pricey. The probes by themselves will cost somewhere between $500 to $1 billion to build. The bigger missions, Constellation-X and LISA, are in the $2 billion range. So the entire suite would cost, if we wanted to build all of them and start today, we'd probably need to put aside about $6 billion. And it's possible there could be cost overruns. I won't swear to you that everybody would come in on budget. But right now, there has actually been a number of reviews of this stuff, and other scientists like it in other fields. There have been a number of Nobel Prizes, including one to my friend John Mather just last year. So this is the kind of stuff that probably will get done. Right now, we're actually waiting for a report that will be issued by the National Academy of Sciences on September 5th. So next Wednesday is a real nail-biter day for all of us involved in Beyond Einstein. That report will indicate which one a panel of senior scientists, members of, selected by the National Academy, thinks should go first. And that will probably then decide for NASA which one of these missions will go ahead and hopefully start preparations for a launch probably in the middle of the next decade. So the answer is that yes, we will probably do this, although we could certainly use support. So if you ever find yourself talking to a senator or a congressman, please let them know you think this is cool. Or if you didn't think it was cool, don't say anything about it at all. So if you'd like to know more about it, here is the website that has links to practically everything that I've given today, plus lots and lots more. And I'd be happy to take any questions. I know, it's all...
So do we know what the purpose of black holes are? What's their role in the universe?
With their role in the universe, they seem to be the things that are the final entropy buckets for the universe. Black holes have the most entropy of anything in the universe. So if the universe is going to end in anything other than just expanding off into nothingness, then we're probably all going to end up in a bunch of black holes. As to purpose, we don't really know. They're interesting objects. They're incredibly simple. That's the weird thing about a black hole, is that a black hole has two parameters. It has its mass and it has its spin. It sort of has a charge too, but you can basically ignore the electrical charge. So, that's incredibly simple. A hydrogen atom has a lot more degrees of freedom than a black hole. So black holes are these, they're just mysterious objects. We just don't know very much about them in some senses, and we hope to learn a lot more as a result of this. In the back?
I was under the impression that nothing can escape a black hole, but then you showed us this diagram about some waves coming out of the black hole when looked at.
Right.
Yeah.
So the question is, you thought that nothing can come out of a black hole, and that's correct. Once it falls inside the Schwarzschild radius of the black hole, it cannot come back out again. However, the things that you saw coming out of the black hole weren't in fact coming from inside the Schwarzschild radius. They were in fact coming from just outside it. So while it's true that nothing, once you fall in, you can't ever come back. I mean, we're never going to have, for example, a black hole sample return mission to come back and bring a piece of one. But it can come from just outside it. That's even the theory behind, for example, something called Hawking radiation, where you can have particles and antiparticles. One falls in and the other one falls out. It is possible for things to sort of come off of a black hole, but they don't come from inside the Schwarzschild radius. They come from just outside. And that's where the gravitational waves are formed that are coming off of this thing. So there's another question here.
So the spark energy, is that a different type of force?
Yes. Effectively, it is a fifth force. And as if you do a search on recent papers on this field, one of the things that's often used to talk about it is called quintessence, or fifth force. It doesn't really totally blow up modern particle physics to include it. It's just that modern particle physics can't answer the question, what is the energy of vacuum? I mean, vacuum is not, in modern particle, in a quantum mechanical concept, vacuum is not a simple stuff. I mean, I've got a little square here with nothing in it. Well, if you look very, very closely, you'd see particles and antiparticles that are created and then disappear, all in very, very short time scans. And so in order to calculate what the total energy in that is, you have to calculate all the total energy of each one of those little particles and antiparticles that are constantly forming and then disappearing. And you might say, well, it should average out to 0. And effectively, that's what everybody said, was, oh, well, that must average out to 0. Largely because if you do the calculation sort of straight, you end up with it coming out to be an answer that's so much larger than is allowed that the universe wouldn't exist. If you do the problem in a sort of a naive fashion, a back-of-the-envelope calculation, you end up proving that the universe can't exist. So since it does, particle physicists have just assumed for many years that, oh, well, there must be another term that makes it just all go to 0, and therefore the answer is 0. So the answer is sort of like infinitely large or 0. And now it turns out the answer is sort of like very small, but greater than 0. And particle physicists haven't a clue as to why. What would be doing that? But it's a complex question, and nobody has a calculation that shows why this answer should be the way it is. Nobody really knows what it is.
The LISA detector, 3 points.
Right.
Would it have different sensitivity in the plane of the 3 points as it's orthogonal?
Very much so, yes. You're exactly right. The sensitivity curves of what LISA is looking at change dramatically as it moves. And so actually the entire system is designed to orbit in a tumbling end-over-end method in order that it scans the sky and gets roughly equal measurements in all directions. I think 3 is cheaper than 6. Oh, you're right, tetrahedron, sorry, yes. You're right. Actually, David and I were just having this discussion. I haven't checked with the guys yet, but I think that the rationale behind 3 is just getting 3 to work is going to be hard enough. They have to, with LISA, the biggest problem is the noise sources, because they're trying to measure something to much smaller than the diameter of an atom. Anything can contribute noise to this calculation. I believe the number was something on the order of 54 noise terms, potential noise terms that they were following that had potential to be significant. I think 30 of them they thought actually were going to be really important. The other 24 or 26 they were tracking just to make sure they didn't become important. But you can imagine how complicated an engineering problem that is when you've got to worry about all those different terms.
When you're getting down and measuring to that small of a number, like you said that there could be like these cubes of like an ion or
a metal alloy. Yeah.
But there's going to be internal dynamics inside that metal alloy as it is, right? And if you're measuring to that precision, just how do you pinpoint a location of an object to that precision?
The one thing that's helping you out is that you don't care about absolute measurements. It's only a relative measurement. So long as things aren't changing internally on your little metal alloy cube too much on the span of 100 seconds, then it doesn't matter too much. Basically, you can get away with it. Making an absolute measurement of this precision is just impossible. It couldn't be done for the kind of reasons you're talking about. But you can make a relative one over reasonably short time scales. Again, over long time scales, you'd end up with similar kinds of problems. So, any final questions? Okay. Well, thanks very much for inviting me. I've been very nice and for enjoying seeing Google.